Hi, my name is Dennis Trolle, and I would like to tell you about WaterWebTools, which is a series of tools that enable operational forecasting of hydrology and water quality. I am presenting this work on behalf of a team comprising myself, Anders Nielsen, Anders Lehmann, and Christopher Nielsen. But first, just to set the scene, we have water-related challenges that are increasing globally. We have challenges relating to flooding, relating to pollution and eutrophication, and we have challenges relating to drought. And hydrological forecasting systems are becoming essential tools that can assist us in making sustainable decisions and safeguard our water resource, and also help us mitigate impacts of long-term climate change, but also short-term weather extremes. There are also some existing systems which enable operational forecasting. There's the real-time SEEP system, which is a large-scale US-based example of a web-based forecasting tool, which covers the entire US. And this is intended for farmers to assist them in planning for fertilizer, manure, and pesticide application. Similarly, we also have European-scale river forecasting services. Again, they also operate at a very large spatial scale, and essentially a scale which is too large for municipal and utility management and decision-making. And then there are also a number of commercial hydrological forecasting systems which may operate closed-source models or may also require installation and some advanced configuration on the client's computer. So there are no scalable kind of plug-and-play web-based forecast solution that exists for open-source models. So that was the core idea behind WaterWebTools. So I would like to tell you about the main concept of ASAP, or a scalable water prognosis, which is essentially the tools behind WaterWebTools. So our initial idea is that we wanted to produce a web-based system that would provide users with short-term, meaning 1 to 2 weeks of forecasts for hydrology and water quality. It should not require any installation or software expertise to operate the system. And it should be based on open source models, which are freely available, and it should be operated based on globally available weather forecasts. Thereby, the system would be functional for any location in the world. So at the moment, we have built in 3 individual tools into the forecast system. And the first one is what we call ASAP Rule, which is the tool that operates the SWAT plus hydrological model, which gives forecasts for stream flow and indication of risk of rural flooding within the forecast window. Then we have a tool we call ASAP Reservoir, which operates the GOTM-WET coupled hydrodynamic-ecosystem model, which is a model that is highly advanced for lakes and reservoir dynamics. And then finally, we have ASAP Urban, which is based on a tool called Maelstrom, which is specialized for producing flood maps or blue spot maps for urban areas. So who could benefit from such a system? Well, we have users within the agricultural sector, and they use it for making plans for timing of pesticide and fertilizer scheduling, and also for optimizing irrigation amount and timing. Then we have users within the research sector, mainly because they would like to have a platform for experimenting, but also for outreach, demonstrating some of the key outputs from models that they may set up. And then, of course, we have water utilities and also municipalities and regional councils, which can use the system for making decisions about water usage and also for making mitigation of flood risks, and also very importantly for outreach to their end users. And we also have users from the private industry that could typically be consultants that, for example, specialize in application of the models that are compatible with this system. That means that they can increase the value of their model competences and also get additional exposure by plugging in models that they have set up into this system. The core concept of the forecasting system is that you should be able to plug in any number of watershed models or reservoir models or urban flood screening models. And the system should then enable an operational forecast that will download local weather forecast data, format that forecast data as input to the specific model case, run the actual model, send the output to a web front end and produce useful data and graphics for the end user to interact with. And at the moment, we can do this based on two different globally available weather forecast products. So that's the American GFS forecast product, which looks 16 days into the future. We also link up to the Met Office Norway weather forecast product, which gives us forecast data 9 days into the future. But essentially, we can link up to any weather forecasting product if we can get access to that product, for example, through an API. I would like to just acknowledge a few of the projects that have kind of paved the way and provided funding for this development, and that is in particular an InnoExplorer grant by the Innovation Fund Denmark, which enabled the operationalization of many of these models that I've just introduced. But also the Prognos project funded by EU's JPI water program, which focused on short-term forecasting of water quality and essentially allowed us to experiment with many of the core models which are now being operational. And I would also like to just acknowledge the WaterX project, which is funded by JPI Climate. And this particular project focuses on seasonal forecasting. And although the tools available in WaterWebTools do not yet produce seasonal forecasts, we would actually be able to link up to a seasonal weather forecast product and thereby also produce hydrological seasonal forecasts. And this brings me to the live demonstration part of this presentation. You would actually also be able to do this yourself by simply going to the main website, waterwebtools.com. So I will do that now. Here you will be able to read a little bit more about the concept of the different forecasting products. But you simply launch the forecast portal by clicking one of these buttons here. And when you do that, you will get a world map with some icons for areas where there's currently operational forecasts being run. I would like to just demonstrate two brief examples, one being a reservoir forecast for the Richland Chambers in Texas. So here you can see it's an ASAP reservoir product. And then next I will show you a ASAP rural forecasting simulation, in this case for a watershed supplying a drinking water reservoir in China. But you launch the forecast case simply by clicking on open. And it will then zoom to the case, in this case, the Richland Chambers Reservoir in Texas. And then you can interact with the forecast output by accessing this menu bar over here. So click on these lines and you'll see forecasts, in this case of temperature at the surface of the reservoir. And you can look at temperature at any given depth of the reservoir. You can also look at dissolved oxygen and chlorophyll. In this case, we look at the temperature. You can see this vertical line here indicates present time, and then we look at the forecast data in this blue line here. And the blue shaded area indicates the uncertainty of the forecast, and as you can see, the uncertainty kind of expands the further you look into the future. We can also look at profiles, that is data with respect to depth of the reservoir. And again, we can look at temperature, oxygen, and chlorophyll. And in this case, you can see that the reservoir is stratified. So we have higher temperatures near the surface of the reservoir, and as we go deeper into the reservoir, the temperature declines. So it's a stratified system. If we click on this little play button, you would see outputs from the forecast window. And you see in this case, it's hourly outputs. So what you can also see is that the surface of the reservoir heats up during the day and then cools down a little bit during night. If we instead look at oxygen, you can see that if you go deeper than 15 meters into the reservoir, so this reservoir is close to 25 meters deep at the deepest point, but below 15 meters depth, it's completely depleted of oxygen. There's no oxygen left. And if we look at the forecast window, you can kind of see that this layer where there's no oxygen is creeping closer and closer towards the surface. So the volume where there's no oxygen is expanding, which is quite typical for a stratifying system during summertime. Okay. Now I would like to show you an example of the watershed forecasting product, which is ASAP. And I'll show you the example that we have running for China. In this case, a watershed to the Kaiping drinking water reservoir. So here you see an outline of the watershed to the reservoir, and you can see all the rivers that flows into the reservoir system. And you can select any given river in the model setup and click on it, and you will get an indication of the stream flow. Again, this vertical line indicates present day, and here we're looking at the stream discharge in the forecast window. And up here you get an indication of the precipitation forecast, so you can see, at least in this forecast, it will rain pretty much every day for the next 10 or 12 days. What you can also do in the system is you can give warning levels. For example, if you wanted a warning for a particular stream, saying that if this stream exceeds discharge higher than 4 cubic meters per second, then you would like a warning indicated by the system. You can also look at the water balance all the way down to a field scale level. So for example, if you were a farmer in this area, you can get an indication of the soil water content in the forecast time window, which could be useful to plan for harvesting or irrigation. But you also get a complete water balance for that field unit in terms of runoff, how much is running off the surface, how much is running off through the soil profile, and how much is percolating to the groundwater aquifers. You can also look at an animation at the surface runoff, which could be interesting in terms of risk of floods. So we can look at the field level again and look at surface runoff. And now the colors indicate the degree of surface runoff for all the individual fields that's included in the model setup, where the blue indicates very low surface runoff, and kind of green and yellow colors indicate high surface runoff during the forecast window. And this sort of map you can use to get an indication if there's areas within your watershed there's at risk of flooding or increased surface erosion. If you like, you can play with all of these demonstrations yourself by simply going to the WaterWebTools website and then launch the forecast portal, and you will be able to follow all the steps that I have just done on your own computer. So that actually brings me to the end of this presentation. Thank you very much for watching. If you would like more information about the forecasting concepts, or learn more about how you can interact with this forecasting technology, please go to our website and feel free to contact us. Thank you.